Conservation of momentum is what makes a rocket move. Let's take a rocket. You got this rocket sitting here in space, and it's not moving at all, let's say. We're a nice pretend space. It's just sitting there. When you fire off the engines, the rocket starts heading that way. How can it do that? It gets some momentum. It's got some mass and velocity after a little bit of time. Well, it's doing that because out the back, you've got the same momentum. This is the rocket, and this is the exhaust. Mass of the exhaust, velocity of the exhaust, mass of the rocket, velocity of the rocket. You've got the same momentum going out the back that you have going towards the front. So the sum total of the momentum is always zero. And if you were to look at a rocket and the center of mass of the rocket and the exhaust over time, it's still sitting right there where it started. It's never moved. And so this is how rockets propel themselves through space. Our space probes now use what's called an ion drive. What's an ion drive? Well, rather than burning fuel, which they can't do because they're in space where there's no oxygen, unless they take their oxygen with them, rather than doing that, they ionize their fuel. So they create an ion which has charge, right? And then they use the fact that it has a charge to accelerate it using electromagnetics, accelerate it really fast. So the exhaust coming out of one of our space probes is moving very fast, tens of thousands of kilometers a second. And so that, even though it's not using, this is how you keep from using a lot of fuel, right? In a typical rocket, like one launching from Earth, that M is big. Well, in space, with our little space probes, we can't make M really big because you can't take it with you. So what do we make really big? We make V really big. And by making V really big, we get to the same momentum we need to make the space probe move forward. We actually have a simple little formula that gives us an idea of the acceleration you can get out of a rocket. So what are the terms here? Well, we have the velocity of the exhaust. We have the mass of the rocket. This dm, delta m over delta t, is the change, right? Delta m over delta t. That's the rate at which mass is ejected. Right? That's the rate at which you're spinning mass out the back of the rocket. And so your exhaust velocity divided by the mass of the rocket times the rate at which your exhaust is leaving, i.e. the kilograms per second that you're getting rid of, gives you your acceleration. And if you're in a gravitational field trying to go up, you have to subtract out the acceleration of gravity. You can see here, well, for our space probes, the G doesn't matter. The G is gone because you're out in the middle of space. You can see here, VE, making VE large is really important. Making VE large is really important. You can also see here the acceleration will not be constant over time if you were to play with it. Why? Well, you step forward a little bit in time and this mass is smaller. You've gotten rid of some of your mass by shooting it out the back. And so you can actually accelerate more as you go. All right? Hopefully you enjoyed this, and we'll be on to the problems shortly.